Greetings. We will continue our discussion on the electron gas in the Hartree-Fock approximation. We are interested in discussing the free electron gas in the Hartree-Fock approximation and specifically further into the random phase approximation. So, in the last class we recapitulated a little bit our understanding of the Hartree-Fock approximation. We dealt with the n electron Hamiltonian, we added and subtracted this term capital F, uppercase F, and this is the notation that we have used, the sum over all of these F for each particle, and this is the average interaction which takes into account most of the 2 electron interactions, so that the difference between this electron repulsion term and this fourth term is very small, very tiny. So, that is how we built the approximation. Then we stipulated that we have a ground state n electron determinantal wave function, which we represented the ground state as phi 0, and it consists of n, the lowest n occupied states, and our prototype of an excited state was another determinant which we called as phi q. We labeled it as phi q to distinguish it from the ground state in which just one electron is promoted to an excited state, and the electron which is promoted is the one which was in the pth state, which is why the ground state phi 0 was also labeled as phi p. So, phi p and phi 0 both represent the ground states. Phi q is the excited state in which just one orbital is different, all the remaining n minus 1 orbitals are essentially the same, and this is the frozen orbital approximation that we are using. Now, our variational function would be a mix of this ground state, which we believe is the ground state, and if it were not to be the best ground state, then it would need to be an admixture of this state and some of the excited states, the prototype of which is phi q, the mixing coefficient being epsilon, which would be a tiny number, and subsequently we sought the limit epsilon going to 0 to demonstrate that this is in fact the variational best state, best self consistent field state according to the variational principle. Now, Fermi correlations are of course included because we are using a determinantal wave function. So, all the statistical correlations are included and all the Coulomb correlations are excluded because that is built into the frozen orbital approximation. Now, we have certainly discussed this in the previous course, which is the special topics in atomic physics. In unit 4 we discussed some of these details, and I will draw your attention to that particular course, and in particular I will draw your attention to what we call as the Hartree-Fock equation as it appears on slide 104 of the unit 4 of this course. Okay. So, this is available at this link, and this equation is what we obtained in considerable detail in our previous course, and if you remember, this relationship which we call as the Hartree-Fock equation was arrived at, it emerged as the condition that the expectation value of the Hamiltonian in the n electron state is a minimum according to the variational principle, subject to the constraint that the 1 electron spin orbitals which go into the Slater determinant are normalized and orthogonal, right. So, those were the constraints. So, with reference to that constraint, how would you get a minimum of the energy functional? The condition that you would get a minimum was expressed in terms of a certain condition that will have to be satisfied. This condition is the Hartree-Fock equation which we find over here, and this is in the notation of the previous course. So, this is the Hamiltonian that we used, which was the sum of the 1 electron part and the 2 electron part. The 1 electron part had the kinetic energy term and also the potential energy in the field of the nucleus, and then you had the electron Coulomb repulsion term. Now I am going to change the notation a little bit and rewrite this equation, and it would not have mattered, but I want to bring the notation very close to what we find in the book by Reims, Many Electron Theory, because it is the notation of Reims that we are going to carry forward for the development of the Feynman diagrams, okay, and for the discussion on the random phase approximation using the Bohm-Pines formalism, for example, we are going to be using the notation of Reims. So I am going to rewrite this equation first in the notation of Reims, and that is a very simple exercise. All you do is to change I to P, J to I, and U to psi, R1 to R, and R2 to R prime. Okay. So it is a very simple, change of notation. So we do that and rewrite this equation. So now you see that you have this F1 operator, and instead of Ui R1 you have psi P of R, because I has gone to P and R1 has gone to R. Okay. So this is just rewriting the same Hartree-Fock equation in the notation of Reims, and then you have the Coulomb and the exchange terms also rewritten. So we will work with the Hartree-Fock equation in the notation of Reims. This is what we have got, and you have the Coulomb and the exchange terms put together in this bracket. I will now separate them. So the Coulomb term appears in the first bracket and the exchange term appears in the second bracket. Now all of these terms pop up at the click of the mouse, and I think it is not an issue because you do not have to write down these things. PDF copy of these slides is available on the internet, you can download it and you can get all of these relations. So you do not have to spend time writing these relations, as you are well aware. So do not worry that okay, all of a sudden a whole integral with 3 psi functions in the integrand, and it takes a certain while to write it down. So do not worry about all that, they will keep popping up at the click of a mouse, because then we can cover a lot in just one lecture. Okay. So if you have any difficulty, you have to raise your hand and stop me. Okay. So you have this 4-dimensional integral. Essentially there are 3 integrations over the continuous space variables x, y, z, or r, theta, phi, or whatever coordinate system you are using, and then a explicit sum over the discrete spin variable is also implied in this 4-dimensional integral. Okay. So we consider non-ferromagnetic systems that you have got an equal number of spin up and spin down states like a closed shell atom. Okay. And you have energies which are doubly degenerate. So you have got one eigenfunction for spin up and one for spin down, and the ground state Slater determinant wave function is a set of these 1 electron orbitals. You have got these n orbitals, but psi 1 up and psi 1 down are degenerate, psi 2 up and psi 2 down are degenerate, and you have psi n by 2 up and n by 2 down. So those are, you have a total number of n by 2 energy states, each being doubly degenerate. So here we are, we have these integrals inclusive of the summation over the spin variables. So let us go ahead and carry out the summation over the spin variables explicitly, okay, and leave the integration over the space variables is undone at this point. So when you carry out the discrete sum over the spin variables, you will have twice I going from 1 to n by 2, okay, because there is no spin dependent term in this operator here. So notice that the sum over I which went from 1 to n now goes from 1 to n by 2, but you have a factor of 2 over here for the Coulomb term, okay. And for the exchange term you will have not this factor of 2, but just the sum over I going from n 1 to n by 2, because whenever you do not have parallel spins, this integral would vanish because of the Kronecker delta MSI MSJ that we are well aware of. Okay. So, now you have got this factor of 2 over here and with the Coulomb term, but the exchange term does not have that factor, and you have got the upper limit of the sum going from going from 1 to n by 2. Then again the integration variable xi was a set of 4 coordinates, the 3 space coordinates and 1 spin coordinate, but now this summation over the spin has been carried out. So, now you have only the space coordinate, namely the position vector r coming over here, and so instead of psi p xi I now write psi p r, okay, and likewise instead of this psi I xi I write psi I r for exactly the same reason. So, this is our Hartree-Fock one electron self consistent field equation that we obtained very extensively in the previous course, and now it has been rewritten in the notation of the book by Reims. So, I bring it to the top of this slide now, and you have this term E square over r is E square over distance, this is the Coulomb term. So, this is the Coulomb interaction which I now write as V r comma r prime, okay, and instead of this E square over the distance I write the term V r r prime here and also here, okay. So, it is really nice that this entire equation comes at the top at the click of a mouse, otherwise it would take that much time to write it on the board, and we can then do less in an hour than what we are able to do now. So, this is the Coulomb in the exchange term, and this is in the notation of Reims. You will find this in the book by Reims called Many Electron Theory, and in the edition which I have got, it is equation number 323 page 53. So, you can follow the book by Reims as well. Okay. Now, let us write this in the second quantized formulation. You will remember that when our Hamiltonian was written in the first quantized formulation, in the first quantization notation, it had this form. When this was the Hamiltonian, the second quantization form was essentially this. Okay, we dealt with this term quite extensively in our previous classes. Now, our Hamiltonian is not H0 plus H prime, because what we have done is to add and subtract this capital F, okay. To this Hamiltonian we have now added this capital F, this is the term in blue, and we have subtracted the corresponding term in this, okay. So, now we can very easily, without going through a very detailed analysis, quickly write the corresponding Hamiltonian in the second quantization notation. So, instead of this term in the second quantization notation, instead of this f, you have got the sum of the little f and the uppercase f, because these are the one electron operators. The one electron operators are now little f plus the big F, the capital F, right. So, this is the term that takes place of the first term here, and instead of the second term which was only this, you must subtract the corresponding term which was added extra over here, okay. So, that is all there is to it. So, now we just exploit the analogy and write this Hamiltonian in the second quantization form in a very neat and very quick manner. So, here we are, we have got you will remember that we made use of the eigenfunctions of the single particle operator to have this determinantal eigenfunctions, and now we are adding and subtracting this capital F and subtracting you are adding it here and subtracting it here. So, now you will also remember that in the previous class we had shown that F was chosen to get self consistent field variational functional minimum such that its matrix element in the state Q and P, P is the ground state, Q is the excited state with just one orbital occupation changed. What the state psi p was occupied in the ground state, now its occupation number is 0. Instead it is the occupation number of psi q which is equal to 1. So, the matrix element of the operator f in these two states is given by this. This is the relationship that we discussed extensively in our previous class, and using this we write these. This is written in the Dirac notation. I have spelled it out fully as integrals. Okay, it is the same term, but so you have got the sum over I going from 1 through n, which is here, and then you have these 4 dimensional integrals inclusive of the summation over the spin variable. And now I am doing a little bit of rearrangement of the term. You have both the terms are double integrals, integrations over xi1 and xi2. Okay. So, I sandwich the integration over xi1 in the middle and pack all the terms in xi1 in this inside term. So, outside this bracket there is nothing with the argument xi1, it is all packed inside this term. Likewise, all the integration over the xi2 is packed inside over here, and outside this bracket there is nothing which has for its argument xi2. So, it is the same two double integrals which are rewritten slightly differently in a mathematically consistent manner for certain convenience, as will become obvious very shortly. And before we get to that convenience, we play this trick. The xi1 and xi2 are dummy variables, and if you interchange them in all the terms, then you are okay. Okay, you can't interchange in one and not in the other, but if you interchange them consistently throughout, then you have no difficulty at all. So, we interchange xi1 and xi2 in the exchange term and rewrite this expression in the box, which is what we have got, and it comes happily at the click of the mouse. Okay. I am so happy not to be required to write this full expression on the blackboard, because that would take really that much time, and sure enough I would make some typographic error and write R1 instead of R2 or vice versa, and we could lose some more time in that. So, I think this is really very nice that we can carry on, and it should not cause any inconvenience to you, because all of these expressions are available to you directly. Okay. So, here we are, we have got these two terms, we have now interchanged xi1 and xi2. Okay. And now we get the summation over I going from 1 through n, integration over xi2, and all the integration over xi1 is inside this beautiful bracket, which begins over here. There are two terms in this beautiful bracket, the beautiful bracket ends over here. The two term, the first one is coming from the Coulomb, the second is coming from the exchange. Okay. So, that is what we have got. In this term in the red box, the only difference from the previous expression is the fact that the summation over I going from 1 through n does not affect anything over here, because the only I dependent terms are inside this beautiful bracket. Okay. So, the only terms which have anything to do with I are inside this beautiful bracket. So, I bring the summation over I, this symbol over here, just behind this beautiful bracket. Okay. And now what does it tell us? What is this? This is an integral over xi2 of psi q star xi2, and then you have got this term, which is just the integration notation of the Dirac matrix element phi q f phi p, that is it, right. So, this is just the Dirac notation, this is the corresponding de Broglie Schrodinger full integral expressions, and if you compare this with the Dirac notation on the left side, you immediately recognize that the result of the operation by the operator f on phi p is given by the summation over I going from 1 through n and this term in the beautiful bracket. Okay? So, it is just a immediate translation from the Dirac notation to the integration notation. Clear enough? Murthy, got it? Yeah, it is just this f phi p, right. So, that is what we have over here, and I have now written it at the top of this slide. There are two terms, so I write them separately one more time. Okay. It is nice to do this, go back and forth, because then it gives you some flexibility on rearranging the terms. So, now once again we rewrite them as two separate terms, and you will see why. So, now we carry out the summation over the discrete spin variables. So, this is d4 xi 1, this is d4 xi 1 as well, which means that it includes the discrete summation over the spin variable. We carry out this discrete summation explicitly as before. This becomes twice summation I going from 1 through n by 2 for the Coulomb term, okay. And for the exchange term it goes as summation over I going from 1 through n by 2, because all the components which are contributing to the summation with spin up and spin down, those will go to 0 because of the orthogonality when you carry out the summation, right. So, now we have a fairly compact expression in which the summation over the spin variable has been carried out, and now this f psi p has been spelled out over here, and you have these two terms over here. So, you have got the one electron operator psi p, that is just the Hartree-Fock equation that we are working with. We are rewriting it in equivalent but more convenient forms. Okay. So, there is no new physics which is emerging as yet, but it soon will. So, we are equipping ourselves with a certain notation which is convenient for us to develop subsequent analysis of the random phase approximation. And if you now do a little further transformation of variable, what you have done is, in this term you recognize that instead of R2 you have used R, and instead of R1 you have used R prime. So, there is variable integration not over R1 but integration over V prime, and this is integration also over R1 which is over V prime, and here the argument R1 is replaced by R prime and R2 by R. Okay. So, it is just a matter of change of some notation. What does it tell us? This term is nothing but f operating on psi p of R2, which is what we have just seen in the previous slide, and therefore, this whole term which is inside this closed loop, okay, is nothing but f operating on psi p. So, now we write this Hartree-Fock self consistent field equation in terms of what we see at the bottom of this slide, and essentially you have got the sum of the one electron operator. This was the little f, this is the capital F. So, it is the sum of f plus capital F, the small f plus the capital F, which is operating on psi p of R, and the right hand side is epsilon p psi p of R. Okay. So, this is just the Hartree-Fock equation, but now we are going to use this further. Mind you, this epsilon I had come as a Lagrange multiplier in the Hartree-Fock theory. This is what looked like the eigenvalue of the Hartree-Fock equation. We know the Hartree-Fock equation is not an eigenvalue equation, it has the resemblance of an eigenvalue equation, but all those details we have discussed in the previous course. So, I will not go through it, and it is that epsilon I which had appeared as a Lagrange multiplier in the Hartree-Fock formalism, for which enforce the constraints that the individual spin orbitals are orthogonal and normalized. So, it is that epsilon I which is appearing over here, and this is the energy functional. But then we also know from the previous class and specifically from slide number 14 that you have this eigenvalue equation for the one electron operator F plus uppercase F, right, and in terms of this epsilon I, this would be the eigenvalue because F plus F is diagonal in this basis, okay, as we have seen earlier. So, since F plus F is diagonal in this basis, then the energy functional E n becomes the summation over epsilon I, but epsilon I is the sum of these two terms. So, I have got the sum of these two terms, and then you have got the two center terms, which is the Coulomb and the exchange, and then you must sum over I and j both. Normally you would have excluded j equal to I, but now you do not have to, because for I equal to j the Coulomb and the exchange terms cancel each other. Okay, so, this is the expression for the energy functional. Okay. These are the two center terms in this red loop. We also know that the energy functional is given by this expression. Okay. So, we combine these two results by identifying the two center terms. Okay. So, the energy functional which is equal to this term which is here plus this term in this red loop, but what is in this red loop is here, which is equal to what is in this blue loop here. Okay. So, whatever is in the red loop can be replaced by what is in the blue loop, because they are completely equivalent. So, I have this energy functional equal to this term which is the matrix element of the one electron operator little f, and then you have got the term corresponding to what is inside this blue loop, and what is inside this blue loop is this minus E n. Keep track of the sign here. So, the minus E n comes here and the other two terms come here. Okay. We should be careful that we carry the minus sign behind E n correctly. So, there we are, you have got the minus E n here. So, I can take this minus E n to the left hand side, that will make it twice E n. Okay. And if you now write this expression for E n alone, then on the left hand side you have got E n equal to half times this term and this term, right. So, that is our expression for the energy functional. It is half of I going from 1 through n matrix element of the one electron operator F plus I going from 1 through capital N, and these are the Lagrange multipliers of the Hartree-Fock theory. Okay. Now, what we are going to do is to develop the Hartree-Fock self consistent field for FEG, which is my abbreviation for the free electron gas. Okay. So, now we are not going to work with the atom anymore. The atom of course has n electrons, and these n electrons are not free, they are bound to the nucleus by the nuclear potential. Okay. So, we want to develop the Hartree-Fock self consistent field expression for the free electron gas, and this is the case for which you can actually obtain analytical solutions. This is the only many electron system for which you can get analytical solutions. For the atomic case you do need the numerical solutions, and our understanding of a free electron gas is that the potential V must be 0. Okay. A free particle is one which is in no field which can bind it. So, V must be 0. So, if we are to apply to electron gas in metals for example, okay, which is what Bohm and Pines worked with. If you are going to work with that, then you know that in a metal you have got these positive ions, positive nuclei in the lattice, and then there are these valence electrons which are not bound to a particular site, but they are free to travel in the rest of the solid. Okay, so that is the model that we have got, but the whole system is electrically neutral. So, we are going to work with electron gas, but we are going to work with a neutral system, not a charged system. If you just work with n electrons, then the total charge of the system would be n times the electronic charge. We are going to work with a neutral system like what you have in a block of a metal. Okay. So, we do have a neutral system in this block, but then we also have these positive nuclei which are at the lattice side. So, how are we going to handle them? Because we want to work with the free electron model, and we know that the nuclei are there and we need them to be there because it is their presence which will make the whole system electrically neutral. So, we need them to be there. So, what we will do is we will smear this charge, and Ashish, are you listening there? This is the Gellium model, Ashish.
Yes,
You are going to smear these positive charges. Okay, you are going to smear these positive charges in this entire volume, okay, in a uniform Gellium type configuration. So, how we do that is like this, that if you have got these jelly beans, okay, you can smash them and make some sort of a Gellium like this, right. Okay, you mean do not get tempted by the jelly beans at the nice attractive desert. So, that is not the idea, but this is in fact called as the Gellium potential. What you do is you take all of these positive charges and smear them out in the entire configuration space. So, you have an electrically neutral system, but the positive charge is not confined to any particular site, it is smeared in the entire region, and you will see very quickly how this allows us to deal with the n electron free electron gas very shortly. So, what we are going to do, the free electrons will be like plane wave solutions. Okay. So, this is like a quasi bound state, and we will work with box normalization, okay, because the free electron states will have the general form, they will be sinusoidal, right. They will be like you can write them as e to the I k dot r. These are travelling waves, plane wave solutions for a free electrons, right. So, that is the nature of the solution that we are going to work with, but then what we will do is we will normalize them according to box normalization. So, these are like quasi continuous spectrum. Okay. So, that is the model we have. So, you have got this box, a positive charge density in which a total charge n times the electronic charge divided by the volume of the box, that is the charge density, and this charge density is uniform throughout the box. Okay. That is the model that we have got, that is the Gellium model that we have. Now, we will use the box normalization condition, and we know we can easily determine how many wavelengths will fit into the box, because here I have got a picture of just one wavelength fitting into the box, but you know that a certain integral number of wavelengths can fit into the box, and this gives you the quantization of the wave vector. Okay, this condition tells you that k must be 2 pi times n over L, and this is for the dimension x. Okay. You will have similar relation for y and z, and the complete expression for the quantization of the k vector will have nxex plus nyey plus nzez multiplied by 2 pi over L. So, this is the usual box normalization that we use, and with reference to this you have plane wave solutions e to the I k dot r, and the normalization will be 1 over root L cube, as we all do in our first course in quantum mechanics. Okay. So, you have got the orbital part, you have got the spin part which is chi of zeta. So, this is the spin orbital that we shall be working with, and if you now have a free electron wave vector in the direction k, then what we can do is count the number of states. The easiest way to do it is to construct a grid of points labeled by integers. So, you have got the 0 over here, okay, and then you put another one on coordinate axis 1, 2, 3 and so on, right. So, these are just numbers, but they give you a counting capability of the number of states in the Fermi sphere. So, you have got a grid of points which are pinned down by integers along x, y and z axis, and then you put them at intermediate locations also, like at coordinates 1, 1, 1, 1, 1, 2, 1, 2, 1 etc., and fill up the whole space by these dots, right. And the number of occupied states are all those which satisfy this relationship, right. And what you do is to all the occupied states lie within a Fermi sphere in which you have got the lowest states occupied in the ground state. Okay. So, that is the Fermi sphere. So, this is our picture of the lowest occupied free electron plane wave states. So, all of these are e to the I k dot r type solutions. There is of course a spin part and there is the normalization 1 over root L cube. Let us look at the Hartree-Fock equation now. This is the kinetic energy term, this is the potential energy term. For the atomic case, what was this? This was minus Z E over R, because it was attractive, it had the minus sign, and then you summed over all the n electrons. Okay. So, that was the situation in the atomic case. In our free electron gas, you do not have the minus Z E over R interaction, because the charge is not localized at a nuclear site in the lattice, it is smeared over the entire space. Okay. And that is what is represented by the potential V of R. So, it is an attractive potential because it is generated by the positively charged nuclear lattice, but it is not located at the nuclear sites, at the lattice sites, but it is smeared over the entire space. And then the other thing we know about it is that it is uniform. So, this is the attractive Gellium potential, this VR psi PR. Okay, this is the attractive Gellium potential. This term over here is the electron-electron Coulomb repulsion. This is the exchange term, the last one. Okay. And now what would you think? That this is the Coulomb repulsion term, it is the electron-electron repulsion term, and there are a total of n electrons, and as much as there are n electrons, there are n positive charges which make the whole system electrically neutral. So, there is as much of repulsive interaction of the Coulomb type as there is the attraction between the Gellium potential and the n electrons. Essentially what we are observing is that these two terms in this little box VR, this is the Gellium potential attraction term, and this is the electron-electron Coulomb repulsion term. This is the Coulomb repulsion term, right, VR comma R prime. So, these two terms are exactly equal and opposite. They are exactly equal and opposite, because this is smeared out over entire space, this is integration over whole space dV prime, okay, and this has no reason to be anything other than uniform density, and therefore, these two terms will happily cancel each other, exactly cancel each other, there is no approximation here. So, the Gellium positive potential cancels the electron-electron repulsion, but only the Coulomb part of it, the exchange term which was over here has to be carried forward, and now our relationship that we have to work with is this kinetic energy term which is here, and then we have this exchange term with sum over I going from 1 through n by 2, okay, and then you have this exchange term over here. The right hand side remains just as it is. The Coulomb term has cancelled the Gellium attraction. So, now we are no more working with atoms, we are working with a free electron gas like what you have in a metal, okay. And this is the kind of system for which Bohm-Pines developed their approximation to deal with the Coulomb correlations. Okay, so here we are. So, this is our Hartree-Fock equation in which the Gellium potential and the Coulomb terms have cancelled each other. You will also remember from our previous course that we had introduced the exchange operator. The exchange operator, and I will not spend any time discussing this, but I will refer you to lecture 23 of unit 4 of the previous course, which is the special topics in atomic physics. And in this we had introduced the exchange operator, and this exchange operator has got this result that when it operates on this, you get this particular term, and if you now sum over I, you have got the left hand side which has got the index I for a particular state. So, you sum over all the n electrons, you carry out the corresponding sum on the right hand side, and in the right hand side you have got this integration over q prime. Integration over q prime again includes integration over 3 space variables and discrete summation over the spin variable. So, when you carry out the summation over the spin variable, you will have these Kronecker deltas, okay, MSI, MSP, and that will reduce this summation from I going from 1 through n to 1 to n by 2 because of this Kronecker delta for spin up and spin down, and you have this result that the exchange operator operating on the orbital psi p of q is given by this sum. So, I will now use this result. This is the result that I now want to use. Notice that this term over here, the right hand side of this, is nothing but the exchange term over here, okay. It is exactly the same, it is absolutely exactly the same. So, you can rewrite the Hartree-Fock equation along with the exchange operator. So, you have got the kinetic energy term, and instead of this you now write it in terms of the exchange operator. You have got the minus sign over here. So, it comes with a minus V exchange operator here. The right hand side is epsilon p. What is this epsilon p? This is the term which can be traced to the Lagrange variational multipliers of the Hartree-Fock theory, right, in the diagonal form. So, you have got the minus V exchange term over here, and instead of this minus V exchange we use the notation F instead of minus V. Now, that is a small notational compromise we make to bring our expressions in line with what we find in the book by Reims. Okay. So, you have this kinetic energy operator plus the F exchange operator, because the Reims exchange operator is defined as the negative of the exchange operator that we had used in the previous course. So, that is the only reason why we had to go through this exercise. So, you have got this kinetic energy operator plus F exchange operating on psi p, and this is nothing other than the Hartree-Fock equation itself. So, we are just playing with the Hartree-Fock equation, but rewriting it in different forms which are convenient to us, and in particular we have now specialized it, we have moved away from the atomic case and we have specialized it for the Gellium potential for free electron gas in a metal. Okay. So, this is what we have got, and this energy of course depends on momentum. So, instead of momentum I write it in terms of the momentum vector k in units of h cross. Okay. Instead of the momentum p, I am using k as the quantum label. So, this relation has been written or rewritten in terms of the quantum labels k rather than p. It is essentially the same expression, but written in terms of k. And each of these, there is a psi here, there is a psi here, there is a Coulomb interaction here, and there is a psi here, and each of these are plane wave solutions which are box normalized. These are I e to the I k dot r. Okay. They are not atomic orbitals anymore, these are plane waves which are box normalized. So, each spin orbital is a plane wave which is box normalized, it has got an orbital part and a spin part, and these are the orbital parts of these equations. So, now let us write this exchange term, what is in this red loop, and I include the minus sign in the red loop. So, I first place that minus sign over here, and there are these 3 wave functions, wave orbitals. One is here which comes with a complex conjugation, then there is a psi k and there is a psi k prime over here. So, psi k prime, let me write as it is, which is 1 over root of L cube e to the I k prime dot r 1, right. So, that is psi k prime. Now, these two, this one is without the complex conjugation and this is with the complex conjugation. So, this comes with e to the I k minus k prime dot, what is the argument here? It is r 2 in both the cases. Okay. So, it is e to the power e to the power I k minus k prime dot r 2. So, these are the 2 wave functions. You have got the 1 over r 1 2 over here, or e square over r 1 2, which is v. So, the e square is here and the 1 over r 1 2 is here in the denominator. Okay. So, it is the same term, but this is what I will refer to as the exchange term coming from slide number 57, and I will be referring to this in subsequent classes also. So, I am identifying this whole term in this red loop as the exchange term from slide 57. Okay. So, keep track of this and we will be using this expression in our subsequent discussion again. Mind you that this sign has been appropriately carried over here, okay, because if we lose the sign, it is very easy to get into a mess. So, here we are, we have got this red loop inclusive of this minus sign, you have got this exchange term, and this exchange term, now all I have done to go from this blue box to the last term at the bottom is to multiply and divide it by this wave function, which is 1 over root L cube e to the I k dot r 1. So, that is also a spin orbital, as you can see, and all I have done is to multiply and divide by this. So, I am still all right. Okay. Now, having done that, I can combine these two terms, this term in the numerator and this term in the denominator, because both have got in the exponent a dot product of 2 different wave vectors with r 1. This is k prime dot r 1, this is k dot r 1. So, essentially this will be k prime minus k dot r 1 if you bring this to the numerator, right. So, this will be k prime minus k dot r 1 or minus of k minus k prime dot r 1. So, that is what we have got. Okay. Are we all together? It is simple, but not keeping track of the sign can make it very messy. So, we have got the exchange term of slide 57, which we have now written as this. Okay. Are we all together? Good. So, you have got k minus k prime r 2 minus r 1 here, okay. And now this integration is over r 2 to we pull out the terms in r 1 outside the integration, which is e to the power minus I k minus k prime dot r 1, okay. Now, notice that what is in the square bracket contains integration over R2. Of course, it contains R1 over here because the denominator is the difference between the position vector R1 and R2, right. So, once you integrate it out, this term in the square bracket will not depend on R2 at all because R2 variable is integrated out. What will it depend on? It will depend on R1. So, what is inside this bracket, this square bracket, is now a function of R1 alone, and that function is what I call as phi of R1, whatever it is. Okay? It has nothing to do with R2 because R2 has got integrated out, and now this exchange term is written as minus e square over L cube sum over k prime e to the power minus I k minus k prime dot R1. Then there is some function which is essentially this, which is a function of R1 alone, not a function of R2, and then you have got the orbital psi k of R1. Okay? So, this is the result that we have got, and we have essentially written the exchange terms in this. The exchange integral is packed, it is sitting inside this phi, as you can see, and if you now look at this function phi, it is this integration over this. Okay? And what is this integral? This integral can be worked out. It is nothing but e to the power I k minus k dot R1 divided by k minus k prime modulo square. So, this integration can be carried out, and I will leave it as an exercise, and this integration is carried out, you get this result, and you can feed in that result over here, that the exchange term now becomes minus e square over L cube, which is over here, summation over k prime, which is over here, e to the power minus I k minus k prime dot R1, which is over here. Then you have got this phi of R1, which is nothing but this 4 pi e to the power I, this term over here, divided by this square of the difference momentum vector, difference between the momentum vectors, and then you have got this I k of R1 here. Okay? So, you have got e to the power plus I k minus k prime dot R1 here, and e to the power minus of I k minus k prime dot R1 here. So, they multiply each other to give you unity, and then you have a very simple compact relation. Now, you see the advantage of doing what we did, okay, that you have the exchange term as minus 4 pi e square L cube summation over k prime 1 over k minus k prime modulo square times this orbital. Okay. Now, this term in the blue box inclusive of the minus sign is what I write as epsilon k. Now, this is written with a subscript k. The previous epsilon which came from the Lagrange multiplier was written as epsilon with an argument k. Okay. So, epsilon with the argument k is different from epsilon with the subscript k. This is the subscript k. Okay. So, this is not the argument, this is the subscript, keep track of that, and the argument k is here, the subscript k is here. This is coming for the exchange term. So, this is the Hartree-Fock equation for the free electron gas, and now you have got both the epsilons over here. This epsilon has got the argument k, this epsilon has got the subscript k, this is the exchange term, this is the Lagrange multiplier of the Hartree-Fock theory. Okay. So, notice that you have the minus sign here and the plus sign here. It is because we have carried the signs very consistently, and these are the appropriate signs as we should have. You have the kinetic energy operator in the first term, so that will obviously give you h cross square k square by 2m. What else can it give, right? So, you have got the h cross square k square by 2m plus this epsilon k, both are operating on psi k of R1. On the right hand side you have got epsilon argument k multiplying the same orbital. So, you have got this relationship that h cross square k square by 2m, the kinetic energy plus the exchange term is equal to this Lagrange multiplier term, where the epsilon subscript k is this relation. Okay. So, now the next question is how to calculate epsilon subscript k. Okay. That is what we will do in the next class. All right. So, thank you very much for today. If there is any question, I will be happy to take. Question from anybody, anywhere?
Yeah, I just have a comment.
Yes, Jobin.
So we could solve the system analytically just because we had a notion about the wave function, am I right?
Yeah, because what is happening in the Jellium potential case is that the Coulomb term is completely cancelling the attraction term due to the Jellium potential. And the manner in which we introduce the operator uppercase F, okay, our 1 electron operators were written as small f plus the capital F, but we chose the capital F rather smartly. That is what we did in the previous class. We did it in a manner such that we got a particular expression for the matrix element of the operator F in the ground state and any other state which had at least one orbital occupancy different. Okay. Now, as a result of that, we were able to show that the variational function, which was, what was it, phi p plus epsilon times phi q, or was it psi p plus epsilon times psi q, I forget. I think psi p plus epsilon times psi q, right, and we found that in the limit epsilon going to 0, okay, you get a variational minimum. Now, it is because of this choice that we are able to get an analytical solution over here.
Okay.
So, that was a very good choice which has come in handy, and now in terms of the box normalized function, we dealt with the free electron gas free electron wave functions, and now our task is to determine what is this epsilon subscript k which corresponds to the exchange term. So, that is what we will discuss in the next class.